all of that. Good morning. First time to, not to Tucson, but it's my first time attending one of these meetings. I'm kind of blown away. It's a giant thing. All right. It's also my first time using these devices, so I'll do my very best. And let's get started. So this is the first lecture. I actually gave a title to all of my lectures, and let's see if I can follow that very carefully. Let's see if I do it justice. So my first lecture is called the number one. No, it's called tantalizing. Oh. It's called examples. I now realize that I'm going to try to use very short words. Okay. All right. Can everybody read that? Fantastic. So the subject that I want to talk about, the theory of harmonic Maass forms, the theory of quantum modular forms, so on and so forth, can be thought of as, well, what? Can be thought of as an extension of the classical theory of modular forms to the non-holomorphic setting. My guess is that many of you, maybe most of you, have already thought about Maass cusp forms, functions which are non-holomorphic that transform like modular forms. But if that's not the case, and even if it is the case, what I'd like to do is start from the very beginning with 5 very explicit examples of generating functions, and with the assumption that these generating functions are interesting, and then I'm going to tie these examples together to give you 5 working examples of what it means to be a harmonic Maass form. So rather than starting with the definition, I'm going to start with 5 concrete examples. So in this first example, I'm actually not going to start with a harmonic Maass form, but I'm going to start with a function which I think might appear in some of the projects that you'll be hearing about later. And it's one of my favorite functions. Probably most of you know this. One of my favorite functions as a testing ground is the function P of n, which is Euler's partition function that counts the number of partitions of an integer n. The partition function will appear nowhere else in these lectures apart from perhaps this first page. But the point I want to get at has to do with different representations for power series that end up being examples of modular forms and Maass forms. So just to be completely explicit, I think P of 4 is 5. Why? Well, because it is. And if I do it right, I now realize that it's hard to do this. Did you see what I mean? So if you count the number of partitions of 4, there's 5 of them, and P of 4 is 5. And one of the first things you might learn about this function is that it is a convenient generating function due to Euler. So the summation n bigger than or equal to 0, P of n q to the n, is given by this infinite product. The product over positive integers n, 1 divided by 1 minus q to the n. How does this make contact with the theory of modular forms? This makes contact with the theory of modular forms, so it's really interesting right here, in that this formal power series is the same as q to the 1 over 24 divided by the Dedekind eta function. And as you probably know, if you don't, the Dedekind eta function is a weight 1/2 modular form. And infinite products, as they appear in combinatorics and in theory of modular forms, for example, functions like the delta function, can often be computed just because of this kind of device. So throughout, I should just make a note. Throughout these lectures, Q is going to be e to the 2 pi I z. Z is going to be in the upper half of the complex plane. And I'm going to be manipulating functions as power series. All right, great. Now, I want you to forget that for a moment, because the starting point for this lecture is still the partition function, but it's going to be a different representation for that generating function. So less well known. I'm afraid I'm just going to write on this device. Got to make sure the paper's here. So less well known. But it's a very easy thing to check, is that the same generating function, summation p of n q to the n, is given as this very strange power series. It's 1 plus the sum n bigger than or equal to 1, q to the n squared, divided by 1 minus q squared, 1 minus q squared squared, all the way up through 1 minus q to the n squared. So it's less well known that this is also an identity that gives the generating function for the p of n numbers. How do I want you to think of this? This could be thought of as being maybe the first modular prototype, of what we call a basic hypergeometric series. More on that later, but where I'm going with this is going to be pretty immediate. It's going to be pretty clear why I'm interested in starting with this particular function. The reason why I'm interested in this particular function is that if you naively change all of those minus signs to plus signs, just do that, if you change all of those minus signs to plus signs, what you will be coming across is a function that Ramanujan wrote down in his last letter to Hardy. And this is his famous deathbed letter. In this deathbed letter, he defines a function called f of q, which is this tantalizing example. It's the power series 1 plus the sum over positive integers n, q to the n squared, divided by 1 plus q squared, 1 plus q squared squared, through 1 plus q to the n squared. Changing those minuses to these pluses, he found this function called f of q, and this is what he termed and named a third order Mach theta function. And what did he mean by that? Okay. This is going to disappear. This is going to go over here. And this is going to go over there. Let me read to you his words, because right after these words, kind of an amazing set of numerical accidents turns out to be apparent. We're willing to do some calculations. In this deathbed letter, so I'm not going to write this out. I hope you're going to read this. Very nice. It's here. This letter that Ramanujan wrote to Hardy from his deathbed begins with these words. I'm extremely sorry for not writing you a single letter up to now. I've discovered very interesting functions recently, which I call the Mach theta functions. And unlike the false theta functions partially studied by Rogers, they enter into mathematics as beautifully as the ordinary theta functions, which he meant to be a weakly holomorphic modular form. And in this letter, he goes on to say, I'm sending you with this letter some examples, and one of these examples is this function f. Now, what's particularly interesting about what Ramanujan probably was thinking about when he made up this term Mach theta functions is that he had a very clear picture in mind in terms of what the analytic property should be for these gadgets. So this is maybe not so well known to this audience, but these words are fairly famous for people who've thought about these forms. In this letter, he goes on to say, and asks the following question, and I'll just read it to you. He says, suppose that there's a function in Eulerian form. Take that to mean basic hypergeometric series. Suppose there's a function in an Eulerian form, and suppose that at all or an infinity of these roots of unity, you find that, well, let me just paraphrase. So suppose that you have a basic hypergeometric series that has the property that as you approach cusps, roots of unity, the function behaves as if it wishes to be modular. The asymptotic properties as you approach a cusp feel like they're modular, keeping in mind that Ramanujan together with Hardy had just developed the circle method. The question is, must it be basically this? Okay, so suppose that this function in Eulerian form closes as neatly as in the cases of A and B, which means behaves like a modular form. The question that Ramanujan asks is this function, this basic hypergeometric series, necessarily going to be the sum of two functions, one of which is modular, one of which is a theta function, and the other of which is basically a trivial function, a function which is bounded at roots of unity? He says immediately, the answer is that it is not necessarily so, and when it is not so, I call the function a Mach theta function. And this function f, he feels, has this property. He goes on to say that I've not rigorously proved that it is not necessarily so, but I have a number of examples in which it's inconceivable to construct a theta function that cuts out the singularities of this Mach theta function. Those are a lot of words, so what I want to do is tell you how Ramanujan immediately after those words assembles a beautiful example. So to make sense of this, he actually in this letter goes on to give immediately a near miss. A near miss. And this is what's very strange. If you've never thought about this function f of q, the idea that you can attach to it near modular forms is kind of a surprise. So Ramanujan's near miss example corresponds to this weight 1/2 modular form, b of z, which he defines curiously enough in this way. He defines it as 1 minus q times 1 minus q cubed times 1 minus q to the 5th. This is an elementary quotient of eta functions multiplied by this weight 1/2 theta function, where the signs alternate. So up to a power of q, this is essentially a weight 1/2 modular form. It has poles, but up to a power of q, this is a modular form. And what Ramanujan conjectures is this crazy accident. And the crazy accident is this. The crazy accident is if zeta is an even order 2kth primitive root of unity, then the limit as q inside the unit disk tends to zeta radially of the function f of q, oops, that's a q, minus -1 to the k times this function, and I'm going to abuse notation. B of q is b of z, where q is e to the 2 pi I z. He says that this is big O of 1. So if you pick a number like I, zeta equals I, or zeta equals -1, and you approach those roots of unity radially from within the unit disk, these differences tend to be bounded numbers. Here, B is an ordinary modular form. F is this, frankly, this queer power series that seems to come out of nowhere. So let me just show you briefly some numerics, just so that we can make some sense out of what Ramanujan had in mind. And, well, the first numerics would be the first even order root of unity, say -1. Here it is. Can you see all that? So let me first illustrate the fact that we have an exponential singularity as you approach -1. So we're considering radial limits as we approach to -1. So that's evaluating Ramanujan's strange f at points like this, approaching -1. Here you can see the exponential singularity. Just curiously enough, around there you get about negative googol. But what his conjecture says is, for this k, if you happen to add the values of that modular form to f, instead of having these exponential singularities, these functions happen to cancel each other out. So these numbers like negative googol end up being numbers that, instead of tending to negative infinity, look like they're tending to the number 4. Okay. And in the special case of the 4th root of unity, I, in this case, instead of considering the sum of f and b, you consider their difference. F is similarly exploding. The difference of F and B is tending to 4i. And if you repeat these calculations with other even roots of unity, you find amazingly that it does look like this Mach theta function, whatever they turn out to be, have the property that they are doing their very best to cancel out the singularities of this modular form and vice versa. But keep in mind, a paragraph before this claim, he was saying there will be no modular forms that exactly cancel them out. The obstruction to exact cancellation is that sometimes you have to add these functions, and sometimes you have to take a difference. So natural question is, where in the world do these formulas come from? How did Ramanujan find them? And really, what is this saying about the modular forms and their singularities? Where do they come from? So it turns out that's a very beautiful picture that's related to special values of L functions. Everything I just told you about are special values of L functions of various sorts, but in a very strange form. So that's a tantalizing example number one. How do you go about finding values of L functions by measuring obstructions to modularity? All right. So that's example one. Example two is only going to take me a second. So what I want to do is I'd like to consider, and Zagier considered this in his work with Hirzebruch, when they were considering intersection theory on Hilbert modular varieties. Zagier, in this Inventiones paper almost 30 years ago, maybe over 30 years ago, defined a power series, which we usually call G, but I will call it H because it's easy to remember. We defined a power series called H to be negative 1/12 plus the sum over integers n congruent to 0 or 3 mod 4, H of minus n q to the n, where H of minus n, these are the Hurwitz class numbers. So these are the Hurwitz class numbers for discriminant minus n. This is an interesting thing. If you're interested in the Cohen-Leinster heuristics, you might be interested in the proportion of n's for which H of n is a multiple of, say, 5. So despite this very rich theory of congruences, certainly for those of you who will be working with Frank in his work, there's certainly a lot of theorems you can prove about the Hurwitz class number formulas, but it still turns out that for modular forms like this, it's not quite good enough to really approach what we expect to be true in terms of like the Cohen-Leinster heuristics. We are unable to prove that a positive proportion, say, of imaginary quadratic fields have p torsion for odd primes p, and even unable to prove that a positive proportion will fail to have p torsion. These are very difficult problems. So if you're interested in studying the congruence properties of functions like H, well, there's some obvious corollaries that could result if you prove a good theorem. The next example, this is example 3. I think most of you will know it because it's considered a non-example in most texts that introduce classical modular forms. If you define E2 of Z to be 1 minus 24 times the sum n bigger than or equal to 1, sigma 1 of n q to the n, where sigma 1 of n is the sum over the positive divisors of n. And this is something that wishes to be a modular form of weight 2. Not very difficult to correct it to be a modular form of weight 2. So let me just say right here at the bottom that this series is very, very nearly modular. It's nearly a modular form of weight 2. All right. All right. There are only 5 examples, so I'm now going to example 4. Example 4 might be, example 4 does not correspond to a proven theorem. So this is the first example that relates to a difficult conjecture that many people are thinking about right now. And it corresponds to the Matthew group M24. It's one of the sporadic simple groups, M24. And let me define a function called mu to be negative 2 times q to the minus 1/8 times 1 minus the sum n bigger than or equal to 1, a of n q to the n. And the recipe that is used to define this function mu comes from mathematical physics. It comes from a specialization of what we call the elliptic genus. So for any friends of yours who work on string theory, the elliptic genus is kind of a big deal. And it turns out that one very special specialization of the elliptic genus gives this function mu. And what I want to show you about this function mu is a table. So Toby emboldened me. He did a table like this. So I'm going to give you some a of n's now. And for the first few, you get numbers that look like this. The first coefficient turns out to be 45. The second coefficient is 231. The third coefficient is 770. The fourth is 2,277. The last one is 5,976. And you get a very interesting sequence of integers, positive integers, which, just like the coefficients of J in Frank's talk this morning, exhibit sub-exponential growth. Very much along the lines of the kind of formula that Frank wrote down. Why are we interested in these numbers? Maybe none of you recognize these numbers apart from being obviously positive integers. But if you had the atlas in front of you, these integers, a of n's are listed here, are very, what am I doing here? Let me do it that way. These numbers a of n are very famous. Is it kind of hard to see? What can I do to help you out there? Okay, yeah. Well, you know what? Maybe, oh, you're saying this is easier to see. Yeah, I agree. Can you see that? All right. So here again are some of those a of n's. I hope I copied them right. And right below this table, you see the sequence of integers 1, 23, 45, so on and so forth. What are those integers? That is the complete list. That's the complete list of the dimensions of the irreducible characters of M24. It's the complete list. And what you want to see is, well, here I find 45. Here I find 231. Here you find 2,277. Here is 5,976. Those other coefficients which aren't listed on the table continue to be very easy to spot finite linear combinations of these irreducible representations. So my hope is many of you have heard about Borchard's work on moonshine for the monster group, where the coefficients of J are explicit linear combinations of virtual characters for the monster. It's conjectured that the Matthew group has a similar phenomenon, and it's an extrapolation of what I'm showing you here in terms of these numbers. So there is a conjecture, it's very precise, and loosely speaking, it's that the coefficients of the specialization of the elliptic genus gives the moonshine module for the Matthew group M24. And the last example I want to give, and again, my point to start with is that I want to give examples of interesting generating functions in number theory without worrying for the moment what ties them all together. I want to make a web of these functions. All right. So in this last example, how am I going to do this? I'm afraid to do this. Well, I'm just going to start doing this. I have some ugly numbers to write down, but Brunier and I, a few years ago, constructed, and I'll teach you how to construct this. We constructed a function that I'm just going to call g of z, which at first glance looks to be completely uninteresting. It starts out with, well, a q to the minus 1 plus a 1.0267q cubed plus a 1.2205 q to the 4th plus a 1.6909q to the 7th, but then minus 6q to the 139th. All of these coefficients are transcendental. And minus 6 is a nice integer. Let me just go on. Minus 0.831. So literally, I'm not telling you that 1.0267 is transcendental. I'm not going to take the time to write down. Yeah. All right. So you have minus 0.8313 q to the 151 plus a whole bunch of ugly coefficients, minus 121.1944 q to the 815th, but then plus a 312 q to the 823. These coefficients go on forever. And just like this block, all of these coefficients are transcendental. They're provably transcendental, and numbers like 6 and 312 are very, very beautiful integers. So in the theory of modular forms, we're trained to think that they're linear operators that work on finite dimensions of spaces. There usually tends to be some Z structure to these spaces, and because of the operators, you're usually able to prove that reasonable forms tend to have algebraic coefficients, or all the coefficients tend to be fairly transcendental. This function g of z has the property that a density 1 proportion of those coefficients are transcendental, but there are infinitely many integer coefficients. This is going to be related to a modular form, and like I said, a density 1 subset of those coefficients will be transcendental, but there will be infinitely many beautiful integer coefficients. That should already, I think, come as a surprise. And so because of that, the question that I want to raise is, what is the significance? What is the significance of the numbers 139 and 823? What's the significance of those two numbers? A number of us were talking at the last break, Don Blasius and Larry Washington and myself. We were kind of, I can't believe I'm going to say this. We feel old. So the question that I asked, and maybe I really am the 4th or 5th oldest person in here. Well, we don't have to keep track. But the point I want to make is that if you were a graduate student in the late 1980s, you would recognize these numbers. Many of you might not have even been alive at the time. But numbers like 139 and 823 were made very, very famous in the late 80s. Let me tell you why. Well, here's a beautiful fact. The beautiful fact is, let's consider the elliptic curve E over Q, given by y squared equals x cubed plus 10x squared minus 20x plus 8. I hope that's right. The conductor of this curve is 37, so I'm pretty sure Larry now knows where I'm going with this. The minus 139 quadratic twist of this elliptic curve, the rank of the minus 139 twist of this elliptic curve, if you were to take the quadratic twist, is 3. The rank of this curve is 3. Okay, so that was a beautiful thing. So in the 80s, there was this big paper by Dorian Goldfeld giving a procedure for finding an effective lower bound for class numbers for imaginary quadratic fields. And this procedure for finding this effective lower bound depended on what's called the principle of repulsions of zeros of L functions. The idea being, if you could find an L function, for example, for an elliptic curve with a large order of 0 at s equals 1, right? That's not supposed to be allowed to happen if you group that L function together with L functions of, say, Dedekind zeta functions. And what it turned out was, if you could prove the existence of a single L function whose analytic rank was at least 3, you would get this amazing theorem giving lower bounds for class numbers, and it was a big deal. The first example for which the work of Gross and Zagier justified that there is an L function with analytic rank at least 3 is this guy. The very second one that was done in the literature was this guy. So if you're interested in computing ranks of elliptic curves and determining whether derivatives of L functions are 0 or non-zero, somehow it looks like I've produced for you a function called G, where determining the integrality versus transcendence dictates whether or not an elliptic curve has a vanishing central derivative or not. All right. So these are my 5 tantalizing examples. If you're interested in gauge theory, if you're interested in these conjectures of Witten and Moore in terms of computing what are called the Donaldson invariants, it turns out that the moonshine module for M24, we've proven, proves a conjecture of Witten and Moore. So let me go back to that last example. Here is the fact. And the fact is this. If we write down that power series G as q to the minus 1 plus the sum n bigger than or equal to 1 a of n q to the n, and the fact, in a special case of a much more general theorem, the theorem is this. If minus n is a fundamental discriminant fundamental discriminant, and if the sign of the functional equation for the quadratic twist by minus n of that curve is minus 1, then it is true that LE prime of E of minus n of 1 is 0 if and only if the corresponding individual coefficient A of n is an integer. And there's more to this theorem. It turns out that if the derivative isn't vanishing, there's a period formula. And because of this period formula, you can determine that LE minus 1 is a transcendental number. So if you're we'll be talking about this. And what I wanted to begin this talk with is some tantalizing examples. And my hope is that some of these functions would be interesting. And I think they are. So the question for today's lecture is this. What unifies these 5 examples? What subject, if you master, gives you the right to prove theorems about these gadgets? And this subject is actually fairly new. There probably nobody was really thinking seriously about this until about 10 years ago. So there's been a lot of work on it lately. And the theory that I'm speaking about and the definitions I'm going to give are only like 7 or 8 years old. So it's the theory of harmonic weak Maass forms. All right. So what I want to do now is start giving you a few definitions. To be completely frank, the words harmonic weak Maass forms are just fancy sounding words for stuff that I think most of you would have no trouble mastering at least the first examples of in anything more than but a few minutes. Not very complicated. All right, so before I give this definition, I'm going to say something like this. All of these series, all of these 5 examples, so actually I have to do it this way to give you some intuition. All of these 5 examples give rise to harmonic weak Maass forms. By some method of completion. And I think I'd like to explain 1 or 2 of these examples by brute force because it allows me to immediately pass to periods of L functions. So the easiest example of this is in like every book on modular forms. The easiest example is this power series E2, often called a quasi-modular form. 1 minus 24 times a sum n bigger than or equal to 1, sigma 1 of n, q to the n. As I think most of you know, E2 fails to be modular just for reasons of elementary analysis. And how does one fix this? The fix, the completion, is to define a function, say E2 star of z, which we define to be negative 3 over pi times the imaginary part of z plus E2 of z. This function is just barely mildly holomorphic. It's not a Fourier expansion e to the 2 pi I z. It is that plus this very strange piece. It's an easy exercise, and Amanda Folsom has assembled, I don't know, 50, 60, 51, 52, lots of examples. It's an easy exercise to show that E2 star of negative 1 over z is z squared times E2 star of z. And of course, E2 star of z plus 1 is E2 star of z. In other words, this behaves like a modular form of weight 2. but it's a weight 2 modular form once we allow for this mild non-holomorphicity. So this is a very, very easy example of a non-holomorphic modular form. And basically, after that slide, we're going to say that that's not an acceptable harmonic Maass form. That's just not, we're not going to care about functions like that very much. Except for those of you who will be proving generalizations of the work of Gross and Zagier on formulas giving factorizations for differences of norms. So one of the projects we've designed is to study the p-adic properties of Hilbert class polynomials for Maass forms. And it's going to be a beautiful theorem, which is very much along the Gross-Zagier type, if you're familiar with that. A more interesting example is the Hurwitz example, of Zagier. So again, I had h of z, which equals negative 1/12 plus the sum on n. I forgot what I called it, but here it is, h of minus n q to the n. What Zagier proved is that if you define g of z, and this is Zagier's idea, it's kind of brilliant because this idea is really the prototype for a lot of what I'm going to say. This says that h of z is, as a component of this function g, the holomorphic part of this function. So you add to this h 1 over 16 pi times the square root of the imaginary part of z, which we already seen kind of before right here in a similar way. But instead of just adding basically what wishes to be little more than the constant function. So I'll explain tomorrow why this is a constant function. If you add to h 1 over 16 pi root y times the sum over all integers n, beta of 4 pi n squared imaginary part of z, q to the minus n squared, where beta is essentially like a gamma function. It's the integral from 1 to infinity of t to the minus 3 halves e to the minus st dt. If you define g this way, then here's the theorem. Let me not call it a theorem because let me just state it as a fact. And the fact is that this g of z is a non-holomorphic modular form of weight 3 halves on gamma 0, 4. Okay. So what's beautiful about this function is that the two parts of this expansion have the property that they never overlap. If you want to study the class numbers and you know this function g, you can manipulate this function without ever having any fear of having these awful transcendental coefficients getting mixed up with the class numbers. And what's nice about that is, well, this guy is modular. You have a theory of Hecke operators, you have a theory of Peterson inner products, you have a lot at your disposal that you can generalize from the classical theory of modular forms that sheds light on functions like this. All right, so the question is, what is this beta? Or more generally, how do we think of this very strange gadget? And the way we think of this very strange gadget is that this double question mark is literally a period integral. And this is where we'll spend quite a bit of time tomorrow explaining how this works. This is literally, this double question mark is a period integral of the Jacobi theta function, the classical Jacobi theta function. You can kind of imagine where this comes from. You're summing over all integers n, something like q to the minus n squared. What did this beta come from? It just comes from the manipulation of calculating a period integral. All right. So in view of this example, we arrive at a number of natural questions. Let me list them in order. The first question I want to raise is about Zagier's function. If we were to start with Jacobi's theta function, starting with Jacobi's theta, how would we know that information about its period integrals how would we know that information about its period integrals leads to the generating function for class numbers? I'm inverting the theorem that's proven. How would we know, if we were to start with the theta function, that there is a theory that would naturally produce the generating function for class numbers? And more generally, and this is what we want to address, more generally, if f is any modular form, say mk, integer weight, half integer weight, who cares? If f is any modular form, what information is naturally revealed from similar period integrals for f? Okay? And you know what? All 5 of those examples I gave you are answers to this question. The 5 examples I started with are explicit examples of this question. I now understand why I get these comments from my teaching evaluations about the quality of my handwriting. Jared was telling me earlier that I have beautiful handwriting after remarking that, you guys, it was amazing. You might have to have like 10 pens for me tomorrow. I'm mashing this to, yeah, I'm mashing this. All right. So I want to conclude with a definition. I need to offer you a definition. But what I've given you glimpses of is that if you start with a cusp form, say a cusp form of an elliptic curve, there is some procedure that I'm going to teach you that says, out of this procedure of constructing a harmonic Maass form, you will naturally produce a beautiful generating function. And the question is, when you do this, what information have you learned about the elliptic curve that you didn't know before? This is where those derivative formulas come from. And so what I want to conclude with is a definition, maybe a number of definitions. So let me just fix some notation for the rest of all of the talks. This is H. This is going to be the upper half of the complex plane. Throughout, I'm going to let Z be X plus IY, where X and Y are respectively, well, X and Y, real and imaginary parts of Z. And the main player here is going to be the hyperbolic Laplacian operator. I don't know if time will permit. I'm not sure if we'll do some spectral theory of automorphic forms. I realize now I still have a bunch of sheets left and very little time. Think about that. And the hyperbolic Laplacian operator will be defined with respect to any parameter k, which is a real number. It will be this differential operator. We have many identities for this operator, so for those of you who are doing the exercises that Amanda has assembled, you'll develop quite a bit of skill in terms of rewriting such operators in a number of ways, and some commutation relations and some crazy folding types of identities. Hyperbolic Laplacian is this gadget. And loosely speaking, here's a definition. If k, and I'm only going to consider k's that are integers or half integers, if k is in 1/2 z, and all of my examples today have the property that gamma is a congruent subgroup, so if k is in 1/2 z and gamma in SL2z is a congruent subgroup, comma, then a function m from h to c is a weight k, harmonic Maass form, on gamma. If, I'm so tempted to just say if it is, but if 1 m of gamma z equals, well, cz plus d to the k times m for all, well, I'm running out of space, for all a, b, c, d in gamma, but that's the little gamma, that's big gamma. And, well, I'm going to really emphasize that I'm putting quotes here, and that the Laplacian operator literally annihilates this function. I'm going to have to decorate this definition a little bit tomorrow so it becomes useful. But what I wanted to show you is that there's nothing surprising. A harmonic Maass form will be a function on the upper half plane, possibly non-holomorphic, that transforms like a modular form. For those of you who know a lot about half-integral weight modular forms know I'm telling a lot of lies here, but in principle this is correct. And the only thing that we're adding to the classical definition is really our demand that the function be annihilated by this Laplacian operator. So just as a brief preview for the remaining lectures, I guess I'll begin the next lecture with the definition of a harmonic Maass form, or at least the class of harmonic Maass forms that we wish to study. And what I'd like to just give as a preview, I'm not going to write this down, I'll just show this, you don't have to copy this, is that over the course of these lectures, I'm going to talk about Fourier expansions. I'm going to talk about the action of the Hecke algebra. I'm going to talk about this operator called xi. So if you're reading the notes, I want to tell you this operator xik is incredibly important in this subject. It allows you to associate different spaces of these forms. We'll talk about periods and values and derivatives of L functions. And for those of you who are working on the projects, some of you might learn about proving congruences for the coefficients of harmonic Maass forms, either by using Galois representations or by using Borchards products. Some of you, as I said, will be proving generalizations of this Gross-Zagier formula for differences of norms of differences of singular moduli. And I guess that's all I have to say about that. Thank you.